Yeah, good afternoon everyone. Yeah, we will continue the mass transfer operations. So we were seeing this total reflux ratio and minimum reflux ratio. In the minimum reflux ratio, the condition of Q is equal to 1, which is for saturated liquid or liquid at its feed at its bubble point. Okay, we have derived this equation. So Rm for the minimum reflux ratio, to calculate the minimum reflux ratio, we just derived this one. Okay, for McCabe-Thiele method, if you see in the McCabe-Thiele method earlier, so it can't be used, this McCabe-Thiele method. One of the limitations of the McCabe-Thiele method is it can't be used when minimum reflux ratio is less than 1.3 times less than the minimum reflux ratio. At this condition, when our optimum or a operating reflux ratio is less than 1.3 times the minimum reflux ratio, then McCabe-Thiele method cannot be used. Okay, the similar conditions for the similar feed conditions we have to apply. We have to derive RM. Okay, minimum reflux ratio. For the next necessary condition, if you see this one, the next condition is, I think it's Q is equal to 0. Okay, yeah, feed is saturated vapor. Next condition, how to derive the minimum reflux ratio for the saturated vapor. Feed is saturated vapor, or we can say feed is at its dew point. Feed is saturated vapor, or we can say feed is at its dew point. Both are same. For this case, Q is equal to 0 for this case. So on equilibrium diagram, okay, everything is same, x and y. Okay, this is diagonal and this is equilibrium curve. Okay, now first point is, first we have to, before deriving any plates, first we have to just locate our xt value and which needs to be projected up to the diagonal. Then next one is xf we need to locate and project up to the diagonal. Then xw we need to project up to diagonal, xw. All the three compositions we know. Now if you see this one, so operating line for the top section. Operating line for the top section we can derive from this one. Y is equal to r by r plus 1 into x plus xd by r plus 1. So using the intercept, if your intercept xd by r plus 1 is coming in this range, then we can just draw a operating line for the top section. Then Q line equation. Q line equation, you already know this one. Okay, this is okay. If your intercept is ranging like this, okay, so this is operating line for the stripping section. Then from here what you have to do, you have to draw Q line equation. Q line equation, how can you draw? Y is equal to minus q by 1 minus qx plus xf by 1 minus q, I guess. Okay, using this we can draw Q line equation, xf by 1 minus q, or slope of q by 1 minus q. Since here our q by 1 minus q slope is equal to minus q by 1 minus q is equal to q is equal to 0. So 0 by 1 minus 0 is equal to 0. There is no slope. So no slope means for q is equal to 0, it's a horizontal line. Just simply it's a horizontal line for q is equal to 0. Now we have to estimate the slope of the operating line. This one, slope of the operating line, rectifying section operating line. To estimate the slope is nothing but delta y divided by delta x. So for corresponding y value corresponding to this x value is this one, xd, which is projected up to this diagonal. Because of that, both the values will be same, and the corresponding y value is same, x value will be same. And so this one, so if you see, this one is a operating line. and operating line and this operating line and Q line is intersecting here. So here it is intersecting. So we need to project this intersection up to some value x dash, and the corresponding y value on the y is so up to here this is y dash. For example, we are assuming this is x dash and this is y dash. Before that, the q line is like this. So we have taken that value, the intersection value, this side, and this is also this side. So this is delta y, and now this is delta x. So slope for the operating line of rectifying section S is equal to R by R plus 1. So we are calculating minimum reflux ratio, meaning Rm by Rm plus 1 is equal to slope is nothing but delta y by delta x. Delta y is this one, xd minus y dash divided by delta x is this one, xf minus x dash. Now we need to equate these two equations. So Rm into xf minus x dash is equal to Rm plus 1 into xd minus y dash. We just have to just rearrange that one in terms of Rm. So in terms of Rm, how to arrange that? So we just have to rearrange that one. Okay. Not xf. So, okay, this one. Okay. So since we are estimating this one, so this is delta x. This range is delta x because this value we are taking this one. So here this value we are taking this one. So our range needs to be this one, not this one, because we are not taking xf projected to the equilibrium curve. I'm not taking. So this is when this is delta y, then this is delta y. So that is xt minus y dash. Slope will be different. Xt minus y dash. So this is xt minus x dash. So xt minus y dash. Okay. So just we need to expand that one. Rm into xd minus Rm into x dash is equal to Rm into this one xd minus Rm y dash plus xd minus y dash. So this Rm xd and this Rm xd will be cancelled out. So here left out is Rm x dash, which is minus. So this Rm y dash we will bring this side. So Rm into y dash plus Rm into y dash is equal to left out is xd minus y dash. Therefore, we can take common Rm y dash minus x dash is equal to xd minus y dash. Now, what is Rm? Rm is equal to xt minus y dash divided by y dash minus x dash. In this way, we can calculate what is minimum reflux ratio for the case of Q is equal to 0, which is saturated vapor or liquid at its feed at its dew point. Okay, for feed at its dew point, we can calculate, or Q is equal to 0, we can calculate this way. Then the next derivation is for partially vaporized. For the case of partially vaporized, okay, why? Because we are deriving all these equation means depending on the feed conditions, the feed line will be varying. Because of that, the slope of that line will be varying. Operating line will be varying. Then the next case, third case is partially vaporized. Partially vaporized. So partial amount of vapor will be there and partial amount of liquid will be there. For this case, we already know Q value will range in between 0 to 1. Okay, for 0 to 1, same one, equilibrium plot. Equilibrium plot is nothing but between x and y. Then we need to draw diagonal, 45 degrees diagonal, and this is equilibrium curve. Then we have to first locate what is xt, we need to project this xt up to the diagonal. Then we need to just locate our xf. Then we need to project this xf up to the diagonal, and we need to locate what is xw. Then we need to project this xw up to the diagonal. After doing all these things, first we have to do y is equal to r by r plus 1 into x plus xd by r plus 1. Using this slope, we just have to slope value we just have to locate here. Then we can just draw the operating line like this. So operating line for the rectifying section. Then next way is next step is from xf projected up to the diagonal, we have to locate our q line. For q line, for this case 0 to q is less than 1. So that will be looking like this. Okay, for q is equal to 1, it is a straight vertical line. For q is equal to 0, it is a horizontal line straight. And for 0 to 1, in between these values, it will come like this, or it will come like this. In between 0 to 1, it needs to be come. So okay, any one type of we can assume. Okay. So okay, let us assume this one is our q line. So from this q line, first we have to project this x value up to the diagonal to this side. So here also it is projected up to the diagonal, means it is also xd only. Yd is equal to xd, nothing but yd is equal to xd. Now our intersection point is here. Operating line of the rectifying section and q line equation are both intersecting here. From this intersecting point, so we have to locate our x dash value. From the same point, we have to locate our y dash point. So now our slope will be this one. So delta x is xd minus x dash, and delta y is this one, this two, xd minus y dash, which is delta y, this is delta x. The slope already we know, slope is nothing but s is equal to r by r plus 1, this value r by r plus 1. For minimum, it is just our notation scheme is different. Rn by r plus 1 is equal to delta x. Delta x is this one, xd minus y dash divided by xd minus x dash. Same you will get xd minus x dash. So now we have to just expand this one. Rm into xd minus x dash is equal to xd minus y dash into Rm plus 1. Rm plus 1. Then Rm into xd minus Rm into x dash is equal to xd into Rm. Then minus Rm into y dash plus xd minus y dash. So xdrm will be cancelled out. So left out is minus Rm into x dash, and this will come this side. So plus Rm into y dash is equal to xd minus y dash. Then this is Rm we can take common. Then it will become xd minus y dash divided by y dash minus x dash. So for the case q is in between 0 to 1, we can use this equation. So this intersection point is very much important to locate a second point on the x and y graph. Then the next case is q greater than 1, we can take. Okay. Then cold liquid or subcooled liquid. Feed is cold liquid, or sometimes it will be given as subcooled liquid. So okay, in this case we know that q will be greater than 1. So same one, we need to have an equilibrium plot which is in between x and y. So this is a 45 degrees diagonal line, and this is equilibrium curve. And from this equilibrium curve, first we have to locate our xd, and it needs to be projected up to the diagonal. Then we need to locate what is xf. Then it needs to be projected up to the diagonal. Then we need to locate what is xw. We need to project this xw value up to the diagonal. After doing so, by writing the operating line equation for the top section or enriching or rectifying section, we have to draw the operating line equation for the rectifying section, xd by r plus 1. So now this xd by r plus 1 value, which is intercept, we need to locate here somehow. Then just that location, so we'll just meet that both point with a straight line. Then for q greater than 0, our q line equation will be like this. This will come like this. So then after q line, we need to project this xd value to this side. Since it is up to the diagonal, it is also xd, and this is greater than 1. Q is greater than 1, meaning here there is an intersection point between here the operating line intersection is there. So this is called x dash, and from this point we can take this is as y dash. So our delta y will be xd minus y dash, and now this will be our delta x. See, for q greater than 0, it is coming after xf. Before plots, it is coming before xf. All the values are coming before xf. Here for q greater than 0 or a cold liquid, it is coming after xf. So this is our delta x. So slope is equal to r by r plus 1 is equal to rm by rm plus 1 is equal to delta x by delta y by delta x. Delta y is xd minus y dash divided by xd minus x dash. So this one, so we need to expand this one, rm xd minus, and writing direct steps since both are same. So x dash is equal to rm into xd minus rm into xd minus rm y dash plus xd minus y dash. So this one will be cancelled out, and left term rm dash. So this will come that side. So rm y dash is equal to xd minus y dash. So finally rm is equal to xd minus y dash divided by y dash minus x dash. So we are adopting the same notation, y dash, comma x dash, everything. Okay, but values are different depending on the conditions of field. The values are different. This is for q greater than 1. The values of here x dash is different from the values of this x dash here. Okay, depending on which side the q line is lying, depending on where the intersection point is coming, depending on that only we have to, these values will change. Notation scheme we are adopting same x dash, y dash, everything, but these values are not same in every case. In every case, these values are different. X dash and y dash values are very much different. You have to remember that one. Okay. For the sake of derivations, we are using same notation scheme, x dash and y dash. Okay. The last case is this superheated vapor. Okay. So for the superheated vapor. Okay. I request you to please do for this one, superheated vapor. Superheated vapor. For superheated vapor, Q is less than 0. So same one, Q is less than 0 means our our Q line will come like this. So below it will come here from XF, it will come like this. So you need to do this one. So just say what is the equation, final equation after doing so in the next class. I think you understood this one. Anybody is having any doubt, please just say me, otherwise I will continue. Anybody is having doubt? Otherwise, you didn't understand anything. Just please respond. Everybody is sleeping. Yes. Shall I continue?
Yes, sir.
Yeah. Okay. Okay. Then now coming to the PPT. Yeah. Okay. This I have clearly given what is the meaning of these terms in the PPT. So first, if you see how to use this PPT, so at total reflux. Okay, total reflux means we don't have any output and input to this column. So just we will drop some feed inside this one and operate our column. With every part of the product will be recycled back to this column. From the reboiler recycled, from the condenser it is also recycled. There is no product input and product output. So F is equal to D is equal to double G is equal to everything is zero. Then vapors, whatever the vapors are coming, it will be converted into a liquid, and whatever the liquid is coming, it will be converted to a vapor. So Ln is equal to Vn plus 1. Everything will be same. Vapor is equal to liquid. So everything will be same. Just we will operate this column like this in such a fashion so that we will find out minimum number of plates required in the column we can find out. So during experimentation, we will perform this one. If we observe same thing on the equilibrium graph in between x and y, we will found that the minimum number of plates are required, because in the graph paper when you draw for this case you will observe very minimum number of plates, only 3 plates are observed, because the operating line for both stripping section and enriching section will coincide with this diagonal. Because of that we will get a minimum number of plates. So at infinite reflux ratio or a total reflux ratio or a maximum reflux ratio, minimum number of plates are required, and maximum reboiler and condenser duty will be required, because everything whatever the liquid is coming, that will be converted to vapor by this reboiler. Whatever the vapor is coming, that will be converted to liquid by this condenser. So the duty, the heat supply to this coolant supply to this condenser and the heat supply to this reboiler will be very high, because everything we are recycling back. Nothing, we are not collecting any product. So if you collect some product, some duty will be reduced on this reboiler and condenser. So because we are not at all collecting any type of product inside from this side, so we will get a maximum reboiler and condenser heat duty by operating a total reflux condition. Then the minimum reflux ratio. So minimum reflux ratio is, if you see some feed will be just fed down, feed is continuous, feed will be there here. So after feeding, some part of the liquid will be recycled and very minute part will be collected as a distillate. So gradually we will increase our reflux ratio so that it will reach to the total reflux ratio. From the minimum to minimum is 0 up to the maximum R infinity. Up to R infinity we will increase this one. When you do this type of operation, what will happen? The operating line will just coincide with this equilibrium curve. It will come towards the equilibrium curve. Okay, in the previous case, minimum reflux ratio, this operating line, this green line and this violet line will coincide with this diagonal. Because of that, we are getting a minimum plates. When this operating line is towards this equilibrium curve, the plates required will be very high. So 3 plates are coming around in the first section itself. In the next stripping section, more than 5 plates we are observing. So total 7 plates. 7 plates will be used for 7 plates will be used when minimum reflux ratio. The column is operated at minimum reflux ratio. It's just an example, okay? In the real example, it will be many 100 plates like this will be required. So because of this, so at minimum reflux ratio, the number of plates required is infinite or maximum. Okay, maximum that column can be operated, that much infinite plates will be required. And at this minimum reflux ratio, the both condenser and reboiler duties are minimum, because we are extracting some part of distillate or some part of residue from this one, and only the little part will be just recycled back or a refluxed back. Because of this situation, the condenser and heat duty will be very low. So we are saying the heat duty for both condenser and reboiler are minimum at the minimum reflux ratio, but number of plates required will be maximum. Then calculation of minimum reflux ratio. So RM, how to calculate this RM? We are saying for Q is equal to 1, we have to calculate like this way. Q is equal to 1, our Q line equation will be like this. So intersection of this Q line with the operating line of the first enriching section operating line will be taken as some YF, and from this one, so since this is a straight line, we will take this as XF. So after derivation, by equating this slope with Rm by Rm plus 1, so we will get the final Rm value, this one. We just derived this equation, you can verify. Then for next case, Q is equal to 0, or feed is saturated vapor, or feed is at its dew point. Okay, for this condition, the Q line equation will be this like this, the horizontal line. Then this operating line, enriching section operating line will coincide with the Q line equation here. Then we have to just project this value, which is called as x dash, and this value we will call this as y dash. And after equating this slope, the slope of these equations, we will get Rm value. And similarly, in the next case, q greater than 0. For q greater than 0, we will obtain the same one. Q greater than 0 means the q line equation will be like this. Then the first operating line, the top section operating line will coincide here. Then we will project this value to the bottom, which is called as x dash, and to this horizontal way, which is called as y dash. Then after equating the slope of this operating line, green line, then we will get this Rm equation. Then the similar next case is partially vaporized. For partially vaporized field, Q is in between 0 to 1. Then for this, the Q line will be like this, and the coincide. Okay, I forgot to show this wrongly. Okay. Okay. The Q line for this type of case, which is 0 in between, Q is 0 in between 0 and 1. The Q line will look like this. Then the intersection point between the soft section operating line and the Q line will be taken as the major composition. It is projected towards the x-axis. It is called as x dash, and this is projected. The intersection point projected towards the y-axis. It is called as y dash. Then the slope of this operating line, green line, will be equated to the slope Rm by Rn plus 1. Then the final rearrangement of that equation, we will obtain this equation. And the last case will be q greater than q less than 0. Okay, you have to do the task, then let me know what is the equation. Okay, one of the equation is already there for the q less than 0 also. One of the equation you will get from this only. Same equation we can apply. Which type of equation that is, you have to say it to me. Okay, then we will look what is optimum reflux ratio. Optimum reflux ratio. Okay, first we will do the summary discussion for this one. So if you see, this one is total reflux. Okay, then afterwards, this will be minimum reflux. We will do minimum to maximum will go. Okay, this is, you can consider total or infinite reflux, and this is minimum reflux. So in between this will be optimum reflux. Okay, how to fix this optimum reflux, we are going to study. So first point, if you see, so first distinction will be at minimum reflux ratio. Whatever the minimum reflux ratio is there, at minimum reflux ratio, at this minimum reflux ratio, the plates required N will be high or low. If you understand this, you can say the plates required will be minimum or low at minimum reflux ratio. Anybody? Somebody please respond. This is very important topic. Many times they are asking. At minimum reflux ratio, what about the plates, number of plates? We have already shown you this one earlier. See, at total reflux is at which minimum number of plates are required. So at minimum reflux is at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From this also you can say. So at minimum reflux ratio, at which maximum number of plates are required. From Okay, can somebody please respond? What is at minimum reflux ratio, how many number of plates are required? It's maximum or minimum?
Maximum.
Okay, maximum. Then at total?
Minimum.
It is minimum. Okay, it is minimum. Then the next one is, what about the size of reboiler? Size of reboiler. Size of reboiler and size of condenser. Size of reboiler and size of condenser. What it may be? So okay, what is the size of reboiler? At minimum reflux ratio, the size of reboiler will be very low or high? Low. Size of reboiler, because the size is nothing but reboiler means diameter we can take, length we can take. When you just whatever the minimum reflux means, L which is refluxing back to the column will be very low. So the size of reboiler will be very low. Then condenser, when you are just taking some of minimum reflux ratio means some of the product you are taking outside. So minimum amount you are sending inside, meaning on the condenser also it will be very low. Then size of reboiler on the total reflux. Total reflux means you are just not taking anything outside. D is 0. D is 0 means all the part of vapor which is converting is recycled back to the column once again, and all the part of liquid which is coming will be recycled back as a vapor here. So now the condenser and reboiler duty will be very high, very high and high. Then what about the size of column? Size of cylindrical shell or that column. What about the size of column? The size of column, when you are just giving liquid, all the liquid inside, minimum means we have a product outside. So minimum liquid we are giving inside. The size of the column will be minimum or low. When you are giving everything to the inside together with this feed is coming. For example, feed is 1 liter and this recycled liquid is also 1 liter. So 1 liter plus 1 liter will become the more. So size of the column required will be very high when total reflux is very high. So by this we can say what is the fixed cost. Fixed cost. At minimum reflux ratio, what is the fixed cost? Fixed cost will be high because maximum number of plates are required. Here also will be high or moderate something, because here the sizes are increasing, reboiler and everything, though the plates are minimum, but sizes of other utilities are increasing. So we can say this is also high. Then what about the operating cost? Operating cost means heat duty to the reboiler, heat duty to the reboiler, and one other operating cost is heat duty to the condenser. So what type of these two heat duties? Okay, this is size of the column, the design parameter. This is operating parameter. How much heat needs to be supplied? How much heat needs to be supplied in order to vaporize that liquid, and how much heat needs to be supplied to the coolant so that it will condense the vapor to liquid. So how much that is required depends on the operating cost. So these two parameters will comes under the operating cost, whereas these parameters, the four parameters, so this 1 2 3 4, these four parameters will comes under the fixed cost. By doing so, we can say this will be fixed cost will be very high. Then heat duty to the condenser, which comes under the operating cost. So heat duty to the reboiler and heat duty to the condenser will be coming under the operating cost. So operating cost will be very high or low at minimum reflux ratio. Minimum reflux ratio means the some part of that distillate is we are collecting. So minimum amount we are inputting inside. So the condenser and reboiler duty will be, the heat supply to will be very low. At total reflux, okay, minimum number of plates are required at total reflux, but the condenser and heat duty will be very high. This is also high. Then by summarizing this one, we can say what is operating cost, total operating cost. So operating cost will be, operating cost is nothing but this heat duty supplied to the condenser and reboiler. So these two are low. So we can say these two are low because these two are the only operating cost. This will be low, and these two are high here. So we can say the operating cost, the overall operating cost will be very high here. So by this we can say what is total cost. Total cost is nothing but sum of the fixed cost plus operating cost. Fixed cost plus operating cost. So now how this fixed cost, using this fixed cost and operating cost, we can evaluate the total cost. So if you draw a graph, okay, if you draw a graph between number of plates, we are denoting with N. So between number of plates and reflux ratio. Reflux ratio we are denoting with R. So if you draw a plate, first what will happen at minimum reflux ratio, the number of plates required will be very high. This we know the fact that one. Okay, at minimum reflux ratio, the number of plates required will be very high. So this we can say this is minimum reflux ratio because it is very low in the x-axis. Okay, then if you continue to increase the reflux ratio, so increasing reflux ratio is this side. So minimum value will be here and maximum value will be here for the reflux ratio, and the number of plates is minimum here and maximum will be here. So at minimum reflux ratio, the maximum number of plates are required. If you continue to increase the reflux ratio, what will happen? So reflux ratio will be increased means the plates will decrease. So like this, the number of plates required will be decreases. So it will decrease, 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 like this it will go. So this you can say this is maximum reflux ratio or maximum reflux ratio. At maximum reflux ratio or the total reflux ratio, or we can say R total, or we can say R infinity. At R infinity, so number of plates required will be minimum. So at minimum reflux ratio, the number of plates required will be maximum. Can you understand this one figure? Do you understand?
Sir, explain once again, sir.
Yeah, if you see this one figure, so first is the graph between number of plates N and the graph between number of plates and reflux ratio. Okay, minimum reflux ratio means for R, what is the minimum? This one is minimum. Okay, minimum value will come here. For the R, the maximum value will come here. Okay, this is clear, I guess. So number of plates minimum will come here, and for number of plates maximum will come here. Okay, graph this is increasing and this is increasing for the x-axis, this is increasing for the y-axis. Okay, minimum reflux ratio means if you consider this as a minimum reflux ratio, at minimum reflux ratio the number of plates is maximum. You only just said that one in the table itself. At minimum reflux ratio, the total number of plates required will be maximum. Okay, from that condition we are applying to the graph. So at this minimum reflux ratio, the number of plates required will be maximum. If you consider the maximum point is this one, so this will be called as a n max. So in y-axis it is n max. So number of plates will be maximum at minimum reflux ratio Rm. At minimum reflux ratio Rm, the maximum number of plates are required. The statement is this one. So as you continue to increase increase the reflux ratio. So from minimum to starting from the minimum to, if you try to increase this reflux ratio, the increasing order of the reflux ratio is this one. If you try to increase the reflux ratio like this, the plot will come like this. So it will increase up to the maximum value. So maximum reflux ratio is this one. So this one is R max. So reflux ratio is maximum here. Then the corresponding maximum reflux ratio we will get on the y-axis, it is n minimum. N minimum is nothing but number of plates is minimum. From this graph we can say that at minimum reflux ratio the number of plates required will be maximum. At maximum reflux ratio the number of plates required will be minimum. Is it okay?
Okay, sir.
Yeah. Okay, now the plates, you understood this one. Yeah. Maximum, the plates will cost a maximum cost in the distillation column. And the next graph will be, okay, these two graphs are same. Okay, both are same. And the next graph will be in between cost versus reflux ratio. Reflux ratio we are indicating with R. So cost versus reflux ratio. Same applies here, minimum, here maximum. Here cost will be minimum and here maximum will be the cost. So what about if you say the minimum reflux ratio? So if you consider this as a minimum reflux ratio point, and if you consider the other okay, if you consider this as a maximum reflux ratio, same one we are projecting, but the variable is cost here. So this is maximum reflux ratio. How the fixed cost and how the operating cost will vary? So fixed cost is nothing but number of plates plus size of reboiler and column, any other thing, size of reboiler, column and condenser. Okay, it will comes under the number of plates. Then operating cost. Operating cost is nothing but heat duty. Heat duty to both the reboiler and that condenser. Then total cost is nothing but this operating cost plus fixed cost is the total cost. At minimum reflux ratio, what about this one? The total fixed cost. At minimum reflux ratio, what are the plates required? Maximum number of plates are required. Yes, yeah, maximum number of plates are required at the minimum reflux ratio. So if you see the total, what we call, this is minimum reflux ratio line, this is maximum reflux ratio line. So if you see fixed cost at minimum reflux ratio, the required number of plates will be very high. So because of these plates, the cost will be high. The fixed cost will be high. Then the fixed cost will vary as you increase the reflux ratio. The fixed cost will go down because at maximum reflux ratio, the number of plates required will be very low. So because of decreasing the number of plates, the fixed cost will go down. And as soon as you reach some value, it will go once again up like this. Why it will go up? As you increase the reflux ratio, the size of the reboiler, size of this condenser and size of the column will increase. That will add the cost to this fixed cost. So fixed costs are nothing but plate cost plus size of the column cost. Initially, because of this plates, number of plates are very high at minimum reflux ratio. Because of this, the cost will be very high. The fixed cost will be very high. So this pink line is nothing but fixed cost. Because of initial very high amount of plates are required, because of that the cost will be initially high at the minimum reflux ratio. and as you increase the reflux ratio, the fixed cost will be lowered somewhat, and as some value is reached, then it will just go once again increasing order, because the size of reboiler and size of column and size of condenser is increasing. Because of that, it will pass through a minima. Okay, if you see the operating cost at minimum reflux ratio, the heat duty to the condenser and reboiler will be very low. Okay, operating cost, if you see, compared to the fixed cost at minimum reflux, the operating cost will be low compared to this fixed cost, because minimum amount of liquid is just collecting and just sending back to the column. So because of this, the operating cost will be going like this. Okay. Gradually it will continuously increase the operating cost. As you increase the reflux ratio, the heat duty to the condenser and reboiler will be increased. So operating cost is nothing but heat duty supplied to the condenser and reboiler. As you increase the reflux ratio, the heat duty on the condenser and reboiler will gradually and continuously be increasing. Then what about the fixed cost? Fixed cost is nothing but sum of these two costs. So sum of these two cost means, compared to these two cost, the total cost will be high. Okay, the total cost will be high. This is total cost. Then it will also, initially at minimum reflux ratio, the total cost will be very high. See, here it is decreasing and here it is increasing. Compared to this decrease, this is nothing. So because of this, total cost will just pass through a minima. It will also pass through a minima like this. So it will go up to the maximum here. So this is called total cost, and the green line is called operating cost. So sum of this operating cost and fixed cost is this total cost. So now if you see, this is passing through a minima. Now this minima is this one. So okay, the minima for the total cost is this one, and the minima, there is no minima for this operating cost, which is gradually increasing. So you can take this as some minimum, some optimal value. Then this pink color for this fixed cost, the minima is this one. After that, it will increase. This is also minima, and after that, it is increasing. So together, all these things, it is called as a R optimum. The cost, the optimum reflux ratio is at which the total cost will be minimum. Okay, the optimum, in other ways we can say, the optimum cost is at which the operating cost, the sum of the operating cost and fixed cost will be minimum. So this is optimum reflux ratio. Is it okay, this one? Somebody please respond. These are very, very important topics. On the boys side, yes.
Okay, sir.
Yeah, from the boys side, anybody? Confusing. Boys are understanding only. Isaac, Tarun. Anybody from the boys side? Okay, it's up to you whether you are going to respond or not. Therefore, I completed this topic. If you have any doubts, you can contact me. Otherwise, that's the case. Okay, the same graphs which I have shown in the PPT also, you can use this PPT as a source of this information. So, yeah. Okay, so this is optimum reflux ratio. What is the optimum reflux ratio? Any ratio, reflux ratio between infinite reflux ratio requiring minimum number of plates And minimum reflux ratio, which requiring infinite number of plates, is a workable system which requires finite stages for a desired degree of suppression. Okay, any reflux ratio between the maximum reflux ratio and minimum reflux ratio at which the cost and the plates required will be minimum. So that is called as a optimum reflux ratio. At optimum reflux ratio is at which the total cost, sum of the fixed cost and operating cost is minimum. This or optimum is nothing but at which the total cost is minimum, as well as sum of the fixed cost and operating cost is minimum. Usually by the blindly we can take by the blind rule, by the rule of thumb we can take that operating reflux ratio is nothing but 1.1 to 1.5 times of minimum reflux ratio. First, we know how to estimate the minimum reflux ratio. Using all these graphs, we can estimate the minimum reflux ratio. After estimating this one, how to know that operating reflux ratio? What is the operating reflux ratio? Whatever we are getting this RM value, we will multiply this with the within the range of 1.5, 1.1 to 1.5, depending on the conditions. It will be specified in your problem that operating reflux ratio is somewhat in between these two values, 1.1 to 1.5 times of the minimum reflux ratio. They will say the operating reflux ratio is 1.1 times of minimum reflux ratio, or they will say the operating reflux ratio is 1.2 times of minimum reflux ratio. So in that case, R optimum is equal to 1.1 into Rm, or R optimum is equal to 1.2 into Rm. Like this, you have to take this minimum reflux ratio and optimum reflux ratio. Optimum reflux ratio is nothing but at which the particular distillation column is being operated. That is called optimum reflux ratio. Okay. Any doubts? Boys said somebody please respond. Isaac, Ravi. Isaac, Ravi, anybody? Number 17, but boys said it's not there. Number 8. Number 8.
Again, bro.
Number 8.
Sir, present, sir.
Yeah, yeah. Do you understand the lecture here today? Number 8. I'm not calling for the attendance. These are very, very important
Yes, sir.
topics.
Yes,
They are
sir.
asking many times. Okay. Then number 1. Number 1.
Yes, sir.
Understand?
Yes, sir. Once again, I have to watch the
Watch.
video again, sir.
Okay, okay. Please go ahead. Watch one for me. Vansudhara, number 32.
Sir.
Yeah, do you understand the topic?
Yeah, sir.
Okay, no problem in that one.
No, sir.
Okay. Okay, in the next class we will see this efficiencies. The last topic in this one is efficiencies. Okay, types of efficiency. There are three types of efficiencies. We'll discuss in the last class how to improve the efficiency of a distillation column. Then one class will take to summarize all the topics which are covered in this fractionating column or the third unit. Yeah, I hope you understood this one. So, okay, this is one old question paper, not old question paper. Now, supplementary people who are writing this mass transfer one, uh, they have given this question paper. Okay, in the next class, I will just go through this question paper. Okay, this is September 2020 paper, this one. So now they have written some date, I think in the September itself they have written this one. So in the next class I will just summarize this one, how to answer this one. If you see, prove that equimolar counter diffusion, many times they ask this one, DAB is equal to DBA, and we already derived. This problem also, aniline problem, we already solved. What is the rate of evaporation of aniline? Then explain about various mass transfer theories with underlying equations. So film theory, the penetration theory, surface renewal theory, you have to explain. And what is effective diffusivity? This is out of syllabus, multi-component, we don't have, so don't need to worry. And this also, I think we solved a mixture of 40% benzene and 60%. So flash distillation, so flash vaporization, we solved this one. Then difference between this Raoult's law and Henry's law, which one is better applicable to solve it and why? Okay, this is somewhat different question they asked. So instead of just differentiating between Raoult's law and Henry's law, they are asking to uh, which law is better, which is applicable for solvent, and why they are asking. So you just find out the answer. It is very interesting answer. Just find out that one. Okay, in the distillation, okay, one problem was there. Some data was missing. In McCarthy method, they asked. So if you see in the distillation, what is azeotropes? Explain minimum and maximum boiling azeotrope. Okay, you have to explain through Raoult's law what is minimum and maximum boiling azeotropes. We covered this topic. And what is relative volatility? So relative volatility, you need to define the composition in liquid phase to the composition in vapor phase is nothing but relative volatility. And expression, y is equal to alpha x by 1 plus alpha minus 1 into x. That equation you have to write and explain each and every time. Derivation, one derivation will be there, y is equal to alpha x by 1 plus alpha minus 1 into x. The derivation we already done. Then discuss about the steps to determine number of stages by McCarthy method. So every time they are asking this one, discuss about the steps to determine number of stages using McCarthy method. So this one you have to write, and next one, based on this procedure you have to estimate the problem. In this problem, reflux ratio is missing. So how to estimate that reflux ratio? I will say it in next class, and discuss the various efficiencies in distillation column. So efficiencies, overall efficiency, Murphy plate efficiency, point efficiency, we will discuss in the next class this one. So how does heat load of a condenser attached to a distillation column change with increase in reflux ratio? Just now what I am explaining, how the heat load of the condenser is increasing with an increase in reflux ratio. We have to discuss through the graphs, N versus reflux ratio and cost versus reflux ratio, and the heat loads, how it is varying. You have to discuss this. Very interesting questions. You have to concentrate more. In the next class, let me know if you have any doubts.